Right, so this is a quick walkthrough of solution for this makeMontage function that we've been trying to build last time. So I've prepared a couple of things here. So I've downloaded this file from the GitHub webpage, or you can find any other anatomical nifty image in the right orientation. I've made a folder to keep the file, and I'm going to just jump straight in. Right, so I'm going to say make a new script. Actually, what I really want to do is a function, but I don't want to use the default template that MATLAB gives me. I'm going to say I'm going to create a function, and the function is going to be called makeMontage. It will take two input arguments, one called file name and another one called number of slices, where we can specify what's going to happen. I'm going to put some help here, makeMontage, make a simple image montage from 3D data. We can add some more details later, but so for now, who wrote it, when it was, and for what purpose, Daphne class. And now I need to think about what this function is actually going to do, right? So the first thing we need to achieve is load in nifty file. So there's a function available for that in MATLAB. The next thing is we need to think about how to display things. And so I'm going to let you find this yourself, but by looking through the image processing toolbox documentation, but there's a command called montage actually in MATLAB, which kind of does what we want to do. So you can use this to look at sequences of images. So for example, if you have microscope images in a video sequence, or you have a bunch of files in a folder that you want to stitch together in this kind of montage. But actually it already has an example in it for medical image data too. And if you scroll up here, you can see that there's a whole bunch of different ways in which you can use this. And the one we're interested in is a multi-frame image array, which can be a sequence of binary, grayscale, or true color images. So ours are sort of intensity images, and they must be m by n by k, so rows, columns, and slices. So we can actually use this probably for our 3D data set. Okay, so let's switch back and exploit that. So go back to the editor here. So we're going to say use montage function in MATLAB to do the grunt work. Okay. We want to change its default behavior because we don't want to display all of them. So think about how to change number of slices. And we'll see in a minute that there's also going to be a problem with the image values it's trying to display, because it's going to use as the range of colors. It's going to use the minimum value in the dataset and the maximum value in the dataset to determine what's black and white, and that in our case might actually make things look a little bit weird. So image brightness contrast is going to be an issue, as you will see in a second. Okay, so let's tackle the first things here. So given a file name, a piece of text that contains a file name, we can try and load this into a variable here, right? So if we want to load a nifty file, we can use the function nifty read. It takes a file name. But if we just leave it like this, then this information goes nowhere. So we need to make sure we assign that into a variable inside the function here. So I'm going to call this one data. So when this line successfully runs, we're going to load in whatever's stored in the file called file name here, and it will be stored in this variable called data. We can do things like we can check the number of dimensions. So there's a MATLAB function for number of dimensions. If that is not equal to 3, then we have a problem. Okay, so we can actually throw an error here and say, at the moment, we can only handle 3D data. Okay, and that's actually going to interrupt the program. But what this means is if we go beyond here, then we actually have something that's a three-dimensional data set, and we can use this montage function as per documentation and just try and see what happens. So the montage function takes a three-dimensional array m by n by k, which is what our data set actually is, and it displays it. So if I save this function as makeMontage and I try and run it from the command line now, so let me switch over here and I say makeMontage, and I'm gonna call it on using this data set that we have here, 01 underscore FSL underscore 7 underscore 1.nii, and hit return. You'll see actually we get something that looks promising. So it looks like it's a whole sequence of images, but the first thing you'd notice is that the colors are completely bled out, and that's because in our data set there's some pixels that have very high intensities, and so we've only got a limited number of gray values, 255, and so the intermediate range of gray values don't get shown up properly because we need to also display the highest value. Okay, so let me show you a way in which we could fix that. So one thing you could do is you could restrict the values of images that you actually want to display. So what do I mean by that? So if we look at the histogram of all the values that are loaded in, so let me just do the following. Load this, instead of running our function, actually load it into a variable in the workspace. So we now have access to it here, so we can see there's this data set. If I just try and look at the histogram of values, so the way you can do that is call the histogram function. Now the histogram function expects a vector, not a three-dimensional image. So if we want to turn our 3D data set into one big long list of numbers, we can use this convenient shortcut of just using the colon, which turns a multi-dimensional array into one big long list of numbers, a column vector. So that basically is going to be all the pixels in one giant list, and we just do a histogram of that. I don't know what happened there. So, and you can see, actually by default it only uses 10 bins. So if we maybe switch this to 50 bins, you can see that there seem to be some pixels out here that are really, really bright, whereas the most of them are actually around between 0 and 2000. Okay, so how do we concentrate the image display onto the main bulk of the distribution? Well, one thing you could do is you could just take the 5th and the 95th percentile, which is called the robust range of intensities. So the way you do that is use the function percentile, which is from the stats toolbox. Use the same trick. You turn the data set into one big long list, and you indicate the percentiles that you actually want. So in this case, we have 5 and 95. And you can see that the values are 0 and 1284 are the actual values. Whereas if you look at the maximum of the whole data set, it's a lot larger. Okay, so it's like 5,000. So we're wasting our display range on a handful of really, really bright voxels, and it would be much better if we actually changed things to only display between 0 and 1284. Okay, so montage actually has this functionality built in. So if you scroll down here, you can specify in one of those name value pair arguments the display range that you would like to use. Okay, so rather than going by default, it will use the minimum value and the maximum value in the data set, but we actually want to use the 5 percentile and the 95 percentile value to make the display a little bit nicer. So let me switch back to the editor window and fix that. So So let me move that guy up here. So that's fine. So the image brightness, we need to fix this here. So how can we, the idea here is use 5 and 95 percentile values to restrict the display range. So let me call that variable robust range. That's going to store the 5 and 95 percentile values. I'm going to use exactly the trick that we looked at in the command line, which is make one big long list and then just return the 5 and 95 percentile values. So that's going to be a vector of 2 numbers in this robust range. And we can then specify display range in that way. Okay, so if I just pass in, so this is called a key value pair. So the key is going to be display range, and the value of 2 numbers are actually going to be stored in the robust range variable that I just created in the previous step. So let me save this, do home, and then try and run the function that we wrote again. Okay, so see whether that actually works. So puts it up here. And you can now see, if we zoom in a little bit, that it displays the images in a much more reasonable, sensible way. Now, what's the problem here is that actually this is not the slice orientation that we want. We don't want sagittal slices, but we want axial slices. So the reason that happens is because in our data set, the way the images are stored are, so there's I know because I actually ran the scan that there's 160 sagittal slices. So rather than, so the third dimension is in the wrong place here. What we want to do is we want to actually exchange the second and the third dimensions for this data cube to be oriented correctly. Okay, and so the idea here is that we need to reorient the cube of data to get axial slices. It's important to note this will work for this particular data set, but for another a data set that's acquired in a slightly different way, this might be slightly different, so we're going to have to probably fix that. So just to show you that, let me create a variable called data p, which stands for permuted version of this data set. And here I'm going to use the MATLAB function permute, which allows you to change the order of the dimensions. So the simplest case would be if you had a table of numbers with rows and columns. If you permuted the first and the second dimensions, the rows would become columns and the columns would become rows. And this idea extends to higher dimensions as well. So if I give it the data set, I can specify here the new order of dimensions that I would like to have. Okay, so if I put 1, 2, 3, the first dimension is going to remain the same, the second dimension is going to remain the same, and the third dimension is going to remain the same. But if I specify that the first dimension of the new array will be dimension 1, the second one will be whatever the third dimension is in the original data set, and the third dimension is whatever the second one was in the original data set, then in fact we're swapping out the second and the third dimensions in this particular data set. Okay? And just to show you that, if I create a new figure, and display the permuted data set here, so our function will now create two figure windows. Let me just actually close all. So we'll see there's 2 windows now. The first one is the original data set. The second one is the permuted version. And you can see the order here looks correct. Okay. Now, the final step is to specify which slices we want to have. And if we go back to the help here, you can actually, if you read through the documentation in a bit more detail, you can see that the frames to display in the montage allows you to pick a subset of values here. Okay, so if you only wanted, for example, every other slice from 1 to 20, you would just specify that as a vector like this. So in our case, how does that help us? If we go back to the editor here, so I'm going to remove the first one because actually this second one is the one we want to stick with. Permuted data set is in the correct orientation for us. Okay. What we want to do here is we also want to specify the indices, single commas, and which we want to display things. Okay. And so let me call them which slices, okay, to be a bit more explicit. So how do we decide on which slices should we display? We're given a number of slices and we can figure out how many slices there are. Okay, the number of slices that are available in the permuted data set, well, that's just how big the data set is in the third dimension. Okay, so we could say actual n slices, the actual number of slices, is equal to the size of our permuted data set in the third dimension, right? So that's going to return, in our case, how many slices are available. Now, what we do want is we want to have this many slices, however many the user puts in, spaced between the first slice and the actual number of slices that are available. So for example, if the user asks for, e.g. user asks for 25 slices, we need to go from 1 to actual n slices in 25 steps. How can we do this? Well, there's a convenient function called linspace that goes from the start point, in this case the number 1, to the end point, which is actual n slices, in however many steps we want to take, right, which this is 25. But we don't want to commit to the number 25 because the user might ask for something else. So I'm just going to actually put the number that they ask for there in n slices. And now the only issue here is that, for example, if we just do this example here, if I use linspace from 1 to say 255 or 256 maybe in 25 steps. Oops, what happened there? We're going to end up at locations that are not integer values. Okay, so that's going to be a problem because we can go to slice 1 and we can go to slice 256, but we can't go to slice 22.25. That's not a good operation. Okay, so how can we convert those numbers to numbers that are integers? Well, the easiest thing is to just round them, right? So if I use the same thing here, but rather than using the values themselves, but the rounded versions of them, I'm going to get a nice approximation of integer values that are spread equally or approximately equally between 1 and 256 in 25 slices, okay? Plus minus half a slice here and there, okay? So I'm going to use exactly this logic in my function to create this number of so let me just put that in here for posterity. So we actually need to round, okay? So round this. Where should we store that information? Well, we're going to use that which slices name that we've come up with equal to this. And so now we're putting both things together, right? So we're loading the data in, we're figuring out what the robust range is, so we can adjust the display range of intensities. We're going to decide how many slices we're going to have, and we're going to create the indices here. The one thing you have to be careful now, when you call the function, you might also want to check that the person actually gives you an actual number of slices, otherwise you're going to get an error. So just to show you what I mean here, if we call the function like we called it before, it would now throw an error because we haven't provided enough information. But if I, for example, let's just try that with 1, if I only want 5 slices, oops, what happened there? Close all the windows. Do it again. 1, 2, 3, 4, 5, right? So that's quite coarse. Or maybe I want to be a little bit more generous and I want to have 20 slices. We now get this. Okay, so this is a nice wrapper around the montage function that allows us to change how many images are being displayed. And you can snoop around a little bit more and find some other cool options for this montage function too. All right, thanks.